So, we have been discussing this matrix method for looking at optical elements along the path of propagating light ray, and we realized that it is a simpler way of just keeping track of components and seeing what they do and so on. So, let me jump right back into the algebra, because I think it is useful to sort of get done with this and then see what its consequences are. So, if you recollect, we worked out this idea for a plane polariscope, basically the two linearly polarized elements, linear polarizer elements, which we first did using just trigonometric identities. Now, of course, using our matrix method, we realize that you get the same solution for the intensity as before, right. The only thing that you have to keep in mind is of course that you have something that is a complex matrix. So, it has imaginary and real parts, and when you take the intensity, you are basically looking at the component multiplied with its complex conjugate, right. So, that is the only difference. So, what we will do now is we will try to apply this to a circular polariscope, right. So, if you recall, we defined this as similar to what we had before with the P and the A. This, remember, is a dark field. I mentioned this multiple times, because the P and the A are perpendicular to each other, and you now have a quarter wave plate kept at 45 degrees and crossed again. So, if this is axis 1 and axis 2, or what we call the fast axis and slow axis, one case refractive index is smaller than the other, then you have the slow axis and the fast axis kept like this, and then you have again same pi by 4 with the vertical, right. So, now it is easy enough to do if you recognize that the final E out is the matrix for the A. Of course, remember matrix for the A, this was 1 0 0 1 times the matrix for the circular polariscope. So, the matrix for the quarter wave plate QWP. So, I am going to call this M1, and then the matrix for stuff that is going on in between, right, which is M, which was the rotation, retardation, back rotation, and matrix for the quarter wave plate 2, this is quarter wave plate 2, quarter wave plate 1, times matrix for the polarizer times the incident light. So, you have this entire chain, right. You start with the incident light, you pass it through a polarizer, this matrix acts on it, gives you another one coming out, then you pass it through this quarter wave plate, the corresponding matrix M2 acts on it, then you pass it through the object, which has principal directions oriented in some at some angle theta. So, that does something to it, it has a thickness h, right, like we discussed, and then finally you pass it through the second quarter wave plate and you take it out through the analyzer. So, this is really the total chain that is going on. So, if you can get this entire matrix, you know what the final electric field is going to look like, right. You will see that it has two components and you can relate them to the incident components and the parameters that are along the way, right. Okay, so, I think I briefly mentioned last time, you can take for M1, since the angle theta is 3 pi by 4, and sorry, for M2, the first one is 3 pi by 4, it does not matter, you will have one the negative of the other, and the delta, because it is a quarter wave plate, is pi by 2. If you put these values in, you will get a matrix that looks like this. Okay, you go back to the original general expression for M that we had worked out, this guy, and then you put delta equal to pi by 2 and theta equal to 3 pi by 4, and you will get this guy, and you do for the other fellow, which is pi by 2 away from this, right. So, you put theta equal to 3 pi by 4 plus pi by 2 and delta again equal to pi by 2, because still a quarter wave plate, then you will get sorry, there should be 1 by root 2 here, you will get something that looks like this. Again, the relative signs are important, not the absolute signs. So, the first one could be 1 minus I 1 and this could be 1 I 1, does not matter, right. The fact that the two signs are opposite of each other is what is important, they are complex conjugates of each other. Okay. So, the final matrix, if I call this entire chain as let us say MT final matrix or MF, let us call it MF, and MF is basically actually let me call this MF, let me remove this P and A out and let us just call this MF, right, because we can relate this much more easily to what we worked out before for the linear polariscope. So, this MF is basically going to have half times this M1 which is 1 minus I 1 times the M which had the delta and theta inside, cosine, sine, whatever, times 1 I 1. This is what your MF is going to look like. If you simplify this matrix and you apply P is equal to 0 0 0 1 polarized in the y direction and you simplified this, then you will get a final vector with E0x, E0y coming out. Remember, I am not applying A yet, okay. Oh, I am sorry, I think I made a, this A should be 0 here because it is perpendicular, right, it is along the x axis, yeah, please make a note of this. I am not applying A yet, so if I do not do that in general, if I just multiply these 3 matrices out, I am going to get something that looks like this. I would encourage you to try this out, it is just simple matrix multiplication. In the interest of boring you with just simple algebra, I will just skip this step and you should be able to work it out by yourself. Okay. So, this is what you will get at the end of this. Now, if you apply A to this, remember we said A is 1 0 0 1 to this to E0x, E0y, then you will only pick sorry again 1 0 0 0 sorry, then you will only pick out the x component which is this guy. So, you will only get sine delta by 2 e to the power of minus 2 I theta, e power I omega t of course comes from before, and then there are some constants e I y or whatever, I am going to leave those out. Okay. So, this is what you will get. So, now again the intensity, the time average intensity is proportional to the square of this complex conjugate times this. So, it will be sine delta by 2, sine delta by 2, complex conjugate will change this term and this term anyway is going to go away for the time averaging, and these two will of course cancel each other out, right. So, the final intensity that you see in the dark field image for a circular polariscope is given by this, okay. And like I mentioned before, this is independent of theta. Which means in a circular polariscope you will only get isochromatics and not isoclinics. Okay, so you can see that this gets rid of some of that complication. So, now you have a way, if you have a monochromatic source, so you have only one lambda, then now you can use a circular polariscope or this combination of quarter wave plates before and after the actual object to eliminate isoclinics. Okay. So, this comes in very handy when you want to actually analyze the image that you get in a dark field or in a bright field and use that for obtaining the stress values. Now, notice also one more comment is that the light field, if you look at the bright field, so in which case if let me just write that down since. So, this is all for the dark field, for a dark field image. For the bright field, you have the intensity going as cos square delta by 2 by the same logic, again you have cos delta by 2 here, and so this is again independent of theta. So, it does not matter whether you use a bright field image or a dark field image for a circular polariscope, you will never get isoclinics. Okay. Not only that, you also will notice that the intensity goes to 0 if delta by 2 pi is an integer for the dark field and delta by 2 pi let me write it down here. So, the dark field is an integer, so 0, 1, 2 etc., and the intensity goes to 0 for the bright field exactly like it was in the plane polariscope case, half integer. So, the nature of these isochromatics do not really change, right. It is just that the isoclinics are eliminated. So, it is a very clever way of distinguishing between the two. Okay, so, I think with that we have more or less covered the basic sort of equations and the theory that goes behind this entire affair. So, we spent a lot of time building this up and you know with the hope that it is actually useful, and turns out it is, right. So, now we will go out and see how do we obtain the stresses. So, we have done the background work, let us see how we put this to use. And the first time I saw this, it was certainly very clever, it is not something I would have thought of easily, and it is a very simple way of using just these 3 or 4 ideas and exploiting them to obtain the stress field. So, let us say first step, you have an object 2 dimensional stress state, it is loaded let us say in some arbitrary direction. So, it generates some stresses inside. So, it is spatially varying stresses. Okay, everywhere in x y. So, that means that the stress tensor is a function of x y, that is what it means. So, the first step you will do is you will use white light, and remember if you use monochromatic light with a linear polariscope, you can't distinguish the isoclinic from the isochromatic. If you use white light, you can distinguish one from the other, right. So, you start with white light, okay, and let us say I am going to just look at this from the z direction. So, this is a viewing direction. So, I will draw along z, say my object looks like this, it is 2 dimensional, it has these various loads applied to it, whatever, it is in equilibrium. So, there are stresses inside and there is some point x comma y. Okay. The first step is to determine orientation of the principal stress directions. Okay, that is the first step. How do you do that? Well, if you just take any light source, any white light source, and you put a just pick one axis as y axis and one axis is perpendicular to that being x axis, and you put the polarizer along y and you let light pass through. So, light is, remember light is all coming like this is a let us say like a plane source, right. So, light coming like this, light coming like this, light coming like this and so on. Even though I have drawn only one z axis, there are a whole family of z axis parallel to each other. The likelihood that you will get an exact value of sin theta is equal to, or sin 2 theta equal to 0 at the particular point xy is unlikely, right. So, you put that and then you put this and you look at it and you will just get some intensity, some color fringe type of thing at x comma y, right, by default, some random point x comma y inside. So, what you would do then is you take this pair A and P, they are perpendicular to each other, keep them perpendicular to each other and rotate them simultaneously by an angle. Okay, so, you have a polarizer, you have the analyzer, they are always perpendicular, you start rotating them, keep the object fixed, start rotating them. At some point, some fringe will pass through the point xy. Okay. The moment when that fringe passes through the point xy, you know that the orientation of the principal axis is equal to phi, that corresponding phi. So, when a dark fringe passes, remember this is white light. So, dark fringe means isoclinic, right, color fringe means isochromatic. So, when a dark fringe passes through x comma y, the corresponding angle by which you have rotated the polarizer analyzer pair together, again keeping them perpendicular to each other, the corresponding orientation of the principal direction is phi, right. So, if I were to do that here, I will just try to recreate the same object. Okay, this is the object. Initially my polarizer was like this and my analyzer is kept like this, analyzer in front of the object, polarizer is behind it, let us say, and initially it is like this. So, at this point initially it is kept vertical, let us start from first. So, initially my polarizer sheet is kept like this behind the object, my analyzer sheet is also kept like this behind the in front of the object, but the analyzer has this direction, polarizer has this direction, right, and initially at this point I get some intensity, it looks kind of grayish, right, or it looks colorful perhaps at this point. So, I do not know what is going on. Now, I start rotating this pair with respect to this point, of course, right. So, the direction of the polarization is changing, the direction of the analyzer is also changing, and the point at the time, if I rotate by angle phi, now the polarizer direction is like this. The moment I rotate that at some angle phi, when I see a fringe pass through our point, or see a black band, not a colored fringe, but a black fringe pass through the point, I know that now it is coincident with the principal stress direction. In other words, if I were to rotate the object in the opposite direction in this figure, the only time that you will get a dark band is when the principal stress directions coincides with P, because then 2 theta will be equal to sin 2 theta will be equal to 0. So, you can get the principal stress direction. So, if you repeat this for all phi, you can get the entire principal stress orientations for the object, right, for the stressed body. So, now at every point you know in what direction the principal stress direction is, right, you know how it is pointing. Okay, so that is first step. If you have done that step, then you have gone through half the problem. Good. Now, the second step is to get rid of isoclinics, because we have got all the information we have about them. So, we get rid of them because they are no longer useful, right. So, now to do this, of course, you use a circular polariscope, or you put in the 2 quarter wave plates on either side of the object before the polarizer and after the polarizer and before the analyzer. Okay. Now since the I is sin square delta by 2, the isochromatics are not changed, right. It is still sin square delta by 2, delta is still a function. Remember when we did this right at the start, we said delta is a function of lambda and sigma 1 minus sigma 2. Delta is still a function of the same lambda and the same sigma 1 minus sigma 2, they are not changing. So the isochromatics will remain unchanged, isoclinics are removed, right. Now if you put, so at the point let us say at excuse me, at the point x comma y, you place the P along the principal stress directions. So you figure out the principal stress direction at a particular point, you now place the P of the circular polariscope along that direction. So that becomes now your y axis. Okay. Now you do something slightly clever, P becomes like this, your body is like this, you have one QWP here, one quarter wave plate here, and then you have an analyzer, right. So polarizer analyzer, and this is us looking at it. Okay. Now you will still see the isochromatics, right, you will see the fringes, but if you now use monochromatic light, you will get dark bands. So instead of white light, now we use monochromatic light, you will get dark bands, right. That is what isochromatics are for a single lambda, right. So now you rotate A with respect to P by some angle, okay, we will call this beta. Okay. If you remember what we did before for the circular polariscopes, the reason I went through this algebra, you remember this. So you had A MF P for the circular polariscope, right. Now we will do the same AMFP, the only difference being the final E0 bar is again A times MF times P times EI bar. The only difference now is that A is not 1000, but it is at some angle theta, right. So it is going to pick up angle beta, so it is going to pick up some components along beta, okay, and this is then applied to this, right. So you have now a rotated version of the A. So you do this times MF times P, and then to the whole thing you apply 1000 if you want a dark field, right, a dark fringe in the dark field. And this is again, this matrix comes up because the A is rotated by beta with respect to the x axis. Okay. Originally, the angle between A and the x axis is 0. So this matrix becomes the identity matrix, cos beta is 1, sin beta is 0, and you do not really see any effect, but now because that is at an angle, you have to add another rotation matrix in between, and finally the fact that this guy picks up excuse me, the fact that this guy picks up only that component that is along the A direction means that you will have this, right. So if you do this, you can write down, we will call this beta. So let me call this E out along the beta direction, E out along beta plus pi by 2 direction, that is the perpendicular direction, right. So this has the rotation matrix cos beta minus sin beta and cos beta times mf that we had before times the polarizer of course, which was 0001 EIX EIY e power I omega t. Okay, that is the whole chain now. Okay, this is the only new component we have added. This is of course before the analyzer cuts off the component that is perpendicular, but we will come to that at the end, right. So, if you see a dark fringe, then that means that the E0 beta is equal to 0, E0 beta rather, and you can do this matrix multiplication. You already know this matrix, you can multiply that by another rotation matrix, and if you get the condition that you see a dark fringe in the dark field image, then you can show, again I am going to skip the algebra because it is a reasonably straightforward thing to do. You can show that the tan delta by 2 is tan beta, that is what you will get from the algebra. So, this is for the dark field. Okay. So, which means the delta is 2 times beta from here, right. Okay. You can of course add any 2 pi to this, it will give you the same value, but this basically is the fundamental relation. So, by rotating the A or the analyzer various degrees, you can actually get a dark fringe to come over the particular point of interest, and at that point you get delta equal to 2 beta. Okay, so that is step number 2. So, you do this at every point, you will get a spread of delta, spread of betas corresponding to that point, and correspondingly you get delta, right. And remember, delta is a function of lambda and sigma 1 minus sigma 2. So, in actually evaluating delta by looking at beta, and you know beta because you are rotating the analyzer by some angle. So, from there you will get delta, and from delta you will get sigma 1 minus sigma 2 because it is monochromatic light and the wavelength is fixed, right. So, this gives us sigma 1 minus sigma 2. That is step number 2. So, the first step you have got theta, the second step you have got sigma 1 minus sigma 2. So, you have got the orientation of the principal stress directions and you have got the magnitude of the difference between the principal stresses. So, these are two probably more important pieces of information that you can obtain directly from the isochromatics and the isoclinics. Okay. But that is not all, there are a couple of other steps you have to do, right, just so that you complete the entire story. The third step is to remember the ordering of the fringe. Okay. And this corresponds to sigma 1 minus sigma 2, remember that because delta varies as proportional to sigma 1 minus sigma 2. And so, you have to be able to order the fringes, you can actually count these fringes with something called fringe ordering. We will talk about that with an example maybe in the next session, but I will introduce it at this point. So, you have to do counting or ordering of the fringes. Okay. So, if notice also the same thing happens here. So, if delta is shifted or if beta is shifted by pi, then delta will be shifted by 2 pi plus 2 beta, and that will be unchanged, right. So, you can add any integer valued integer multiple of pi and delta will not change, but sigma 1 minus sigma 2 will, because that depends on the tan delta will not change, but the delta will change, sigma 1 minus sigma 2 will change. So, to be able to get a unique value of sigma 1 minus sigma 2, you need to remember the fringe order, right. And this is usually done with the counting technique, and like I said, when we work out an example I will show you how this is done. Okay. And by the way, this method of using this beta is commonly called Tardy's method of compensation. There are multiple ways of doing this. This is the simplest way of doing it. So, this has got a special name. And coming back to this relation, remember that the delta by 2 pi n is, if you go back, it was h c by lambda, c being this c. We will refer to this lambda by c, it's commonly referred to as f sigma. This is a material constant. It is a material constant for a, of course, for monochromatic light for a given lambda, because this c is a material constant, right. So, even if you knew n somehow, you still do not know sigma 1 minus sigma 2, okay, even if you knew h, if you knew how thick the sample was, you still do not know sigma 1 and sigma 2 because you do not know c. So, you have to determine c, right. So, you can get if we know c, or in general, or if we know f sigma, right. If you are using the same wavelength all the time, then you need to get f sigma, and once you know that, you can put that in and you will get the value of sigma 1 minus sigma 2. Okay. And the way in which you obtain this constant f sigma is from a standard calibration procedure. Okay. And this usually involves known loading condition. So, you know what the stress is, and you know what the fringe number looks like, and you know what principal stress difference is, because you know the stress everywhere inside, and you just match the two of them and then you get the value of f sigma, right. That is typically what you would do. Okay. And a standard example for this, you probably have seen this multiple times. If you just Google photoelasticity, fringes, etc., you will see this calibration case come up. This is for a diametrically loaded cylinder, a cylindrical sample or a circular sample, right. You have this, you load approximately a point load at either end of a diameter, and then you will get fringes here, right, and then you use those fringes, you get some fringes whatever like this. I will show you an image of this next week, the next session, and we will actually see how this works, but you will basically get fringes like this, and then you know for this loading condition given a particular load P, you know what the stresses are, you can calculate that from theory of elasticity, right. Of course, this is 2 dimensional. So, you know the stresses everywhere. So, you use this at various points inside or at a single fixed point, typically the center, and you fit the f sigma correspondingly. Okay, that is what you do. So, once you know this, you know the principal stresses, you know the orientation of the principal stresses, you know difference between principal stresses. In most cases, you have to augment this with some physical information about the loading condition to remove certain ambiguity. We will talk about that when we discuss a specific problem, but once you have this entire bit of information, you know the stress tensor everywhere in the body, right. So, it is fairly simple enough to write down the stress tensor at that point, and if you know this for the entire cross section, then you know the stress field, full field stress information under the given loading condition, right. So, that is the basic idea behind using this method. Okay. So, what we will do in the next session is I will work out a simple example. I will show you how this is put to use to obtain stresses in one particular loading condition. I will show you also this diametrically loaded cylinder problem. So, you see what the fringes look like, and you can appreciate what this fringe counting business looks like, and then we will probably discuss a few different other configurations where photoelasticity is also used. We will not have time to delve very deeply into them right now. So, I will talk about this reflected photoelasticity. So, this all this we are talking about right now is transmittance. So, your light is going through the object, it is presumably transparent to optical light in the optical wavelength region, and reflected photoelasticity is a slightly different paradigm. It has its own challenges, we will touch on that briefly, and then we will wrap up this part on photoelasticity with that, right, and then we will move on to full field, full volume reconstruction methods with X-ray tomography or optical tomography.